Hello, everyone. So last time we looked at mean value theorem, which was a very fundamental theorem in calculus. MVT, or mean value theorem, says that if f is continuous on the closed interval a to b and differentiable on open interval a to b, then we can say there exists C between A and B with f prime of C equals f of B minus f of A over B minus A. So f of B minus f of A over B minus A is the slope of secant line connecting the end points of the curve. And f prime of C equals this means one of the tangent lines, at least one of the tangent lines, is parallel to this secant line connecting the end points of this curve. So we saw some applications of this mean value theorem. So we saw some applications. Now today we want to do another important application of mean value theorem, namely increasing decreasing functions. How can we determine a function is increasing or decreasing using mean value theorem and using derivatives basically? How can we determine that? So increasing, so another application, increasing decreasing functions. Increasing decreasing functions. And also concave up and down, we will also cover this. With a trailer full of carrots. So let's start with the definition of increasing functions. We have seen it before, we saw it in pre-calculus. We also reminded you in the first lecture, review lecture. So a function f of x is called increasing if x1 less than x2 implies that f of x1 is less than f of x2 for every x1, x2 in domain of f. So if you want to look at the picture or the graph, so this is an increasing function because any x1 and x2 that I consider on this domain, let's say this is the domain of f, and let's say this is x1 and x2 with x1 less than x2, then I can say that f of x1 is less than f of x2. x1 less than x2 implies f of x1 less than f of x2. This is the definition of increasing function. Okay, so please note that this definition must hold for every x1 and x2 in the domain. Not just for one pair or for some pairs. If it holds only for one pair or for some pairs and not for every pair x1 and x2, then the function will not be increasing. So let me give you the definition of decreasing function as well, then we will see some examples. So similarly, the function f of x is called decreasing if x1 less than x2 implies f of x1 is bigger than f of x2 for every, again, for every x1 and x2 in domain of f, So decreasing function looks like this, any x1 and x2 that I consider, let's say x1 and x2 with x1 less than x2, then I can say that f of x1 this time is bigger than f of x2. So x1 less than x2 implies that f of x1 is bigger than f of x2. Okay. So let's look at an example. Show that, let's say, f of x equals 3x plus 1 is increasing. So how can we show that this function is increasing? We have to apply the definition of increasing function. So let x1 and x2 be two numbers in domain of f, which in this case is all real numbers, with x1 less than x2, then I have to show that f of x1 is less than f of x2. How can I show that? Well, f of x1 will be 3x1 plus 1, f of x2 will be 3x2 plus 1, right? Because f of x is 3x plus 1. So how can I construct f of x1? Well, I have x1 right now. I need 3x1 plus 1. So why don't I multiply both sides of the inequality by 3? So let's multiply by 3. Then we get 3x1 less than 3x2. And then let's add 1 to it. Then we get 3x1 plus 1 less than 3x2 plus 1. And this means f of x1 is less than f of x2, because 3x1 plus 1 is f of x1, 3x2 plus 1 is f of x2. So I started with x1 less than x2, and I concluded that f of x1 must be less than f of x2, and that means f is increasing, hence f of x is increasing. Look, Les is here too. Okay, next example. And consider f of x equals x squared on the, let's say, domain minus infinity to 0. Show that f of x is decreasing. It to the feed wagon. Okay, so I have to show that f of x is decreasing. That means I have to consider 2 points x1 and x2 in the domain. So let x1 and x2 in domain of f, and in this case the question is assuming that the domain is minus infinity to 0 with x1 less than x2. Then what can we say? Then we can say that minus x1 is bigger than minus x2. So you'll see why I multiply. First of all, if you multiply an inequality with a negative number, then it flips the inequality. But why did I multiply both sides of the inequality with a negative number? Because see, I want to construct f of x or f of x1. F of x1 is x1 squared. So you may tell me that, okay, why don't we square both sides of this inequality? But I would say that it's a little bit tricky. We are not allowed to square both sides of the inequality unless both sides are positive. But right now, x1 and x2 are both chosen from the domain, which is a set of negative numbers. The children have come to help too. So I'm not allowed to raise both sides to power 2 right now because both sides are negative, but they have to be positive. But if I multiply both sides with negative numbers, see right now they're original numbers are negative, but after you multiply with the extra negative, they both become positive. And then I can raise both sides to power 2. And minus x1 and minus x2 are positive, or let me say are non-negative numbers. Okay, so the trick here is, yes, I want to raise both sides to power 2, but x1 and x2 are chosen from the domain which is assumed in the question to be the set of negative numbers. So right now I'm not allowed to raise the inequality both sides to power 2. But if first I multiply both sides with a negative number, then first of all, multiplying with a negative number flips the inequality. And after that, I will have 2 negative numbers on 2 sides of my inequality. 2 positive numbers on two sides of my inequality. And now that I have 2 positive numbers, or at least non-negative numbers, now I can raise both sides to power 2. Then we can say that minus x1 the whole squared is bigger than minus x2 the whole squared. Recall, if A is less than B and A and B are non-negative numbers, then A squared is less than B squared, okay? So if you have an inequality and both sides are non-negative, then yes, of course, you can raise both sides to power 2. And right now, minus x1 and minus x2 are non-negative, so I can raise both sides to power 2. I'll get minus x1 the whole squared bigger than minus x2 the whole squared. So what can we say? So we can say that x1 squared is bigger than x2 squared, which means f of x1 is bigger than f of x2. So what did we show? We showed that x1 less than x2 implies f of x1 bigger than f of x2 for every x1 and x2 in domain of f. This means that hence f of x is decreasing. F of x is decreasing. Do you remember what this is? Okay, so now the next example, let's consider the same function. Again, consider f of x equals x squared. Is f of x increasing, decreasing, neither, or both? See, the function is still same as before, but the domain in the previous question was mentioned at minus infinity to 0. But in this question, domain is not mentioned. It just says that f of x is equal to x squared. No mentioning of the domain. So if the domain is not mentioned, from pre-calculus, if the domain is not mentioned, you have to consider the natural domain, which means the largest possible domain for your function. So solution, you need to consider the natural domain for this function for f of x, namely, what is the natural domain for this function? Domain of f equals all real numbers or minus infinity to infinity. The natural domain for polynomials is always all real numbers. Okay, so the domain of this function, or the largest possible domain, or natural domain is all real numbers. Now, on the set of all real numbers, is this function increasing or decreasing, or both increasing, decreasing, or neither increasing nor decreasing? Well, to answer this question, we have to look at the definition of increasing, decreasing. So for example, we want to decide whether this function is increasing or no, but we have to look at the definition. What does definition tell us? Definition says the function is increasing if for every pair x1, x2, if for every pair x1, x2, x1 less than x2 implies f of x1 less than f of x2. But this is not obviously the case here. There are some pairs x1, x2 with x1 less than x2, but f of x1 not less than f of x2. So you can easily see them here. See, for example, let's say this is -4, and let's say this is, well, let's say this is -2. -1. See, -2, so f of x is not increasing since -2 is less than -1, but f of -2, which is 4, is not less than f of -1, which is 1. For a function to be increasing, to become increasing, you need to have f of x1 less than f of x2 whenever x1 is less than x2. But here, -2 is less than -1, but f of -2 is not less than f of -1. Similarly, f of x is not decreasing since, now what pair should I, can I consider as a counterexample to show f is not decreasing? Well, I could show, for example, 1 and 2 here. Right? So 1 is less than 2, but f of 1 is less than f of 2. But for decreasing, you need to have, if it was decreasing, we would have f of 1 bigger than f of 2. But here it's not the case. F of 1 is less than f of 2. So since 1 is less than 2, but f of 1 is not bigger than f of 2. Because f of 1 is 1, f of 2 is 4. F of 1 is not bigger than f of 2. So the function is not decreasing. See, to show that, in mathematics, I always repeat this, to show some statement is true, we need to prove in general, right? So in the previous example, where we wanted to show this function is increasing, we were not allowed to give examples. We could not say, for example, 1 less than 3 and f of 1 less than f of 3, because we want to show the function is increasing. So our proof must be in general. That's why we considered 2 arbitrary points, x1 and x2 in the domain, and we showed f of with x1 less than x2, we showed f of x1 less than f of x2. However, in this example, on the next example also, you wanted to show f is decreasing. Again, we proved in general. But for this example, we want to show f is not increasing. So one counterexample is enough. We don't need a general proof here because we want to show the function is not increasing. If you want to show that a statement is not true in mathematics, one counterexample would suffice. And similarly, to show not decreasing, again, one counterexample would suffice. So we showed that f of x is neither increasing nor decreasing. All right, now the next example, suppose that f of x is increasing on some interval, let's say, on the form, let's say on A to C. And f of x is increasing on another interval of the form, let's say C to B. Show that f of x is increasing on the interval A to B. Okay, so I have two intervals, A to C, and then C to B. Okay, the function is increasing between A to C, also increasing between C to B. And I want to show that it is increasing between A to B. How can I do that? How can I show this? So first of all, this graph is just an example. Again, I'm not proving by sketching this graph, or I'm not proving by giving an example. Okay, so again, proof cannot be done with examples. You can sketch an example just to get the idea if you want, but it's not considered as proof. So this graph that I sketched is just to have an idea that what's going on, but it's not a part of proof. The proof has to be in general, not for a specific function or a specific graph. It has to be valid in general. So I want to show that the function is increasing between A to B. So that means I have to consider like two arbitrary points, x1 and x2, between A and B, with x1 less than x2. And I have to show that f of x1 is less than f of x2. Well, where could be x1 and x2 if I want to consider 2 points x1 and x2 in this interval? What are the possibilities? Well, of course, one possibility is that I can have 2 points here, x1 and x2. Both of them, x1 and x2, could be between A to C. Or another possibility is that both of them could be here, between C to B. These two cases are straightforward. So let me write down. So proof. We want to show that if x1, x2 are in A to B and x1 less than x2, then f of x1 is less than f of x2. Now I can consider different possibilities. So case one, let's say x1, x2, they're both between A to C. With x1 less than x2. Then what can I say? Then I can say that f of x1 less than f of x2, since f of x is increasing on the interval A to C by the assumption my assumption was saying that f is increasing between A and C and also increasing between C and B. So I have two assumptions here. And my goal is to show that it's increasing between A and B. So one possibility is I have two numbers, x1, x2. There are different possibilities. One possibility is that they are both between A and C. So in that case, I can definitely say that f of x1 less than f of x2 because the function is assumed to be increasing on A and C. What is the other possibility? So case two. x1, x2, both between C to B, again with x1 less than x2. Then again, we can say that f of x1 is less than f of x2 Again, since f of x is increasing on C to B by the assumption. So no problem in this case either, straightforward. Case 3, x1, x2, x1. Now case 3, another possibility is that I can have my x1 here and my x2 could happen to be here. That's also a possibility, right? So both x1, x2 do not have to be on the same subinterval. One of them could be in A to C, the other one could be between C to B. So case 3, x1 in A to C, x2 in C to B. And with x1 less than x2. Then how can I want to show f of x1 is still less than f of x2. I'm assuming increasing between A and C, also increasing between C and B. So I have to use that somehow. How can I use this fact? Well, look at this picture. x1 and x2, the green ones. I'm talking about the green ones right now. I cannot compare them directly because I don't know whether the function is increasing on the whole A and B. But I can compare x1 with C, right? Because I know that the function is increasing on A and C, right? So I can compare x1 with f of x1 with f of C. What can I say about f of x1 and f of C? Well, x1 is less than C. So f of x1 is less than f of C, right? So let me write it this way then. F of x1 is less than f of C. Since x1 is less than C. Well, there's just one possibility that if x1 itself is equal to C, because here, remember, I'm choosing x1 between A and C closed interval. So x1 could be C itself as well. And if x1 is C itself, then f of x1 will be, of course, equal to f of C. But other than that, if x1 is less than C, then f of x1, of course, will be less than f of C. So just to make sure that this is valid in general and for any choice of x1, so let me change this one to x1 less than equal to C and f of x1 less than equal to f of C. Right? So x1 most probably in most cases is not C, is less than C. In that case, f of x1 is less than f of C. There's just one possibility that if x1 equals C, then f of x1 will be equal to f of C. Since this and since f is increasing on A and C. Similarly, I can now compare f of C with f of x2. Well, C is less than x2, and therefore f of C is less than f of x2 because, again, the function is assumed to be increasing between C and B. So if C is less than x2, f of C will be less than f of x2. Again, there's just one possibility that C equals x2. In that case, of course, f of C will be equal to f of x2. So similarly, f of C is, I can say, less than equal to f of x2 since C is less than equal to x2 and f of x is increasing on A and C. So what did we show? So we showed f of x1 less than equal to f of c, and f of c less than equal to f of x2. So by the property of inequalities, what can I combine? How can I combine these two? What can I conclude? F of x1 less than equal to f of c less than equal to f of x2. So this of course implies that f of x1 less than equal f of x2. But we have a problem here because I wanted to show that f of x1 is less than f of x2, not f of x1 less than equal to f of x2. So what can I do here? Well, there is only one case. When can I say that equality f of x1 will be equal to f of x2? I want to rule out that, right? So that equality happens if the equality happens here and also the equality happens here, right? So when will this inequality change to equality? If x1 equals c. Let me write this down. So we show this and this. So we can say that f of x1 is less than equal to f of x1 less than equal to f of x2. However, f of x1 equals f of x2 cannot happen. Why it cannot happen? Because f of x1 equals f of x2 happens only if, see, I have two inequalities here. If this changes to equality and this changes to equality, then f of x1 equals f of x2. And that's the only possibility where I can get f of x1 equals f of x2. Because if one of these, at least one of these two inequalities becomes a strict inequality, then f of x1 will be strictly less than f of x2. So the only way that I have f of x1 equals f of x2 is that equality must happen here and equality must happen here as well. If one of these two changes to strict inequality, then f of x1 will not be equal to f of x2. So let me call this one, maybe I can call it star, and call this one 2 star. So happens only if equality occurs in star and 2 star. This happens only if, when can I say that star happens? Remember I explained that. First we had inequality, strict inequality here. Then I had to change it to non-strict inequality just because of the case where x1 equals c. If x1 is not equal to c, if x1 is less than c, then f of x1 will be less than f of c. This will be non-strict inequality only because x1 could be equal to c. So f of x1 will be equal to f of c only if x1 equals c, because if x1 is less than c, f of x1 will be less than f of c. So it happens only if x1 equals c, and similarly for the other one, this equality here happens only if c is equal to x2. Because again, if c is less than x2, f of c will be less than f of x2. So f of c can equal to f of x2 only if c equals x2. So and c equals x2. x1 equals c and c equals x2 means what? x1 equals x2. And this is contrary. This is not possible. Since x1 is less than x2. All right, I was assuming that in the beginning of the problem, see, I was assuming that x1 is less than x2. So we ruled out f of x1 equals f of x2 because we saw that if f of x1 is equal to f of x2, this can happen only if c is equal to x1 and c is equal to x2, and that means x1 must be equal to x2, but I was assuming from the beginning that x1 is less than x2. So we ruled out f of x1 equals f of x2. So we can say f of x1 is less than f of x2. And that's it. So we showed f of x1 is less than f of x2 whenever x1 is less than x2 for any x1 and x2 in between a and b. So that means f of x is increasing on a and b. Okay, now we want to look at the connection of increasing, decreasing functions with derivatives. So theorem, suppose that f of x is continuous on closed interval a and b, and f of x is differentiable on open interval a and b. And suppose that f prime of x is positive on a and b, then we can say that f of x is increasing on a and b, closed interval a and b. So if the derivative of a function is entirely positive on an interval, then f of x will be increasing entirely on that closed interval. F prime is positive on the open interval because the value of derivative is normally evaluated on an open interval. But for continuity, we can also consider on the closed interval. Differentiability always on the open interval. So this is related to derivative. So that's also on the open interval. But increasing, decreasing also defined on the closed intervals as well. On any set, including on closed intervals. So under these circumstances, if f prime is positive for every x between a to b, then we can say f is increasing on the closed interval a and b, meaning that if whenever you have two values x1, x2 chosen from this closed interval with x1 less than x2, then we can say f of x1 less than f of x2. So this is part A of the theorem, and part B similarly, again, if f is again continuous on the closed interval a and b, and f is differentiable on the open interval a and b, and f prime of x is less than 0 on a and b, then again we can say that f of x is decreasing on a and b. Okay, proof. If we do part A, I want to show that f is increasing on a and b. So what should I do? I have to consider 2 points, x1 and x2 on this interval with x1 less than x2. So suppose that, or let x1 less than x2 with x1 and x2 chosen from this closed interval A and B. And what do we want to show? We want to show that f of x1 is less than f of x2. So see, if you look at the x-axis, so you have an a value here and b value here, and then you have some x1 here and some x2 here. Now x1 and x1 could equal to a as well, x2 could equal to b, or they could be both of them strictly between a and b. But in any case, x1 is assumed to be less than x2. So I have some, and the x-axis, I'm just drawing the x-axis, not the whole curve or not on the values on the y-axis, only on the x-axis. I have some values with this order. Now I want to apply MVT. So that's why I'm saying that this is an application of MVT, or mean value theorem. I want to apply MVT for f on the interval x1 and x2. So note that f of x is continuous on x1 and x2, since x1 and x2 is a subset of a and b, right? So if f is continuous on this whole interval, of course, it will be continuous on a sub-interval of that whole interval as well. Similarly, f is differentiable on the open interval. On the open interval a and b. Again, since the open interval a and b is a on x1, x2, again, since x1, x2 is a subset of a and b, again, f is differentiable on the whole interval a and b. So of course, it will be differentiable on the interval x1 and x2, which is a subset of that as well automatically. So we can apply MVT. Thus, we can apply MVT on which interval? On x1 and x2. And conclude that, so if we apply MVT on x1 and x2, what was the statement of MVT? It was saying that f of the endpoint minus f of the starting point divided by b minus a, in this case x2 minus x1, equals f prime of c for some c on the interval. So I conclude that f prime of c equals f of x2 minus f of x1 divided by x2 minus x1 for some c between x1 and x2. Now, what can I say about f prime of c? Look at the left-hand side of this equation, f prime of c. But if you remember, our assumption was saying that f prime, we are proving part A. So f prime of x is positive for every x between a and b. So when it says f prime of x positive on a and b, means f prime of x positive for every x between a and b. Now c is definitely some number between a and b. Now by assumption, f prime of c is positive, since c is between x1 and x2, but x1 and x2 itself is a subset of a and b. and f prime of x is positive on A and B, right? See, here I sketched a graph for you. So C is somewhere here between x1 and x2, but x1 and x2 itself is a subset of A and B, so C is definitely between A and B as well. So we can say f prime of C is positive. Now, if the left-hand side is positive, left-hand side of this equality is positive, of course, right-hand side must be positive as well. So we can say that f of x2 minus f of x1 divided by x2 minus x1 is positive. Now I have a fraction which is positive, and denominator is positive because remember my assumption is x1 is less than x2, so x2 minus x1 is positive. I have a fraction which is positive, denominator is positive, so that means numerator must be positive as well. So x2 minus x1 is positive, so that means f of x2 minus f of x1 is positive, and that means f of x2 is bigger than f of x1 as desired. So our goal was to prove that f of x1 is less than f of x2, or in other words, f of x2 is bigger than f of x1, and we proved it. So we are done for proof of part A. And part B, it's very similar. Let me leave it as exercise. In part B, you can show that, if a function, derivative of a function is negative, the function is decreasing. The proof is very similar to this part A. So let me leave it as exercise. So let's look at an example now. Determine the intervals on which f of x is increasing and intervals on which f of x is decreasing. So part A, let's say f of x equals x squared minus x plus 5. So this is a parabola opening upward because the leading coefficient is positive. So we know that the parabola opening upward, it's like this, so it's first decreasing and then increasing. So we know this from high school or from pre-calculus. We can find the vertex and we can find out on which interval the function is increasing and which interval the function is decreasing. But here we want to do it with calculus. We want to do it with derivatives. Okay, so the theorem said that if the derivative of a function is positive, then the function is increasing. If the derivative of a function is negative on an interval, then the function is decreasing on that interval. So what is the derivative of this function? So solution. F prime of x is 2x minus 1. Now, f prime of x, if you want f prime of x to be positive, if 2x minus 1 is positive, so that means x bigger than 1/2. Similarly, f prime of x will be negative if 2x minus 1 is negative, and this happens if x is less than 1/2. So by theorem above, since f of x is a polynomial and hence continuous and differentiable everywhere. What can we conclude? We can conclude that f of x is increasing on which interval? F of x. F prime is positive if x is bigger than 1/2. So f of x is increasing if x is bigger than or equal to 1/2. Remember that the theorem was saying that, well, of course, for derivatives, we always use open intervals. But for increasing, decreasing, we can conclude them for closed interval as long as we have continuity on the closed interval. And of course, the polynomials are continuous everywhere. So f prime of x here is positive on the open interval 1/2 to infinity, but the function is of course continuous on the closed interval 1/2 to infinity. So the function will be also increasing on the closed interval 1/2 to infinity. So the theorem above, this is also f of x is decreasing on minus infinity to 1/2. F prime positive for bigger than 1/2, so increasing for 1/2 to infinity. F prime negative for less than 1/2, so decreasing for minus infinity to 1/2. Now part B, f of x equals x cubed. So again, if you're familiar with the graph of this function, this cubic function, you know that the graph looks like this. If you're not familiar, that's okay. We will spend some time on graph sketching towards the end of this course. So we'll cover this this type of examples as well. But if you're familiar with this graph from before, you know that the graph looks like this. So as you can see it in the graph, the function is actually increasing on the whole set of real numbers minus infinity to infinity. So let's see whether our calculation and our analysis, whether it verifies this fact that, you know, it's always increasing this function from minus infinity to infinity. So what is the derivative of this function? Derivative of this function is f prime of x, which is 3x squared. Now, when can I say that this is positive? And when can I say this is negative? Of course, x squared is a non-negative function. It can never be negative, right? Any number to power 2 is always non-negative. Times 3, of course, still non-negative. So it cannot be negative. But it might be 0. I need f prime to be positive. Bigger than 0, not bigger than or equal to 0. So when can I say that f prime of x is positive? So f prime of x equals 3x squared bigger than 0 for x bigger than 0, and f prime of x equals 3x squared bigger than 0 for x less than 0. F prime x squared is always basically positive. The only exception is if x is 0, then x squared becomes 0. Other than that, x squared will be always positive. So for x bigger than 0, 3x squared positive. For x less than 0, 3x squared positive. Okay. You can also show this on the real line. This is called sign chart, right? So you can say we can determine the values of x on the first row, and then 0. Here if you want to use sign chart, here you can locate zeros of f prime. And then here you can, in the second row, write down f prime, and in the third row, write down f. So f prime is 0 here, and positive here, positive here. Right? We said that for x less than 0, f prime positive, for x bigger than 0, f prime positive. So this region corresponds to x less than 0. This region corresponds to x bigger than 0. F prime is positive in both these regions, and therefore f is increasing on both these regions. Now, what can I conclude? So, since again, f of x equals x cubed, a polynomial is continuous and differentiable everywhere. By theorem above, we can say that f of x is increasing on, for x less than 0, it's increasing, which means on minus infinity to 0, right? Please remember that for differentiability and for the values of derivative, we use open interval. But once the derivative is positive on minus infinity to 0 open interval, we can conclude being increasing on minus infinity to 0 closed interval according to the theorem. Look at the theorem one more time. Here. Differentiability is on the open interval, the values of f prime on the open interval, but then decreasing on the closed interval. Similarly, for increasing, differentiability on open interval, values of f prime on the open interval, but then increasing on the closed interval. So here we can say increasing on minus infinity to 0 closed interval, and f of x is increasing on 0 to infinity, again closed interval. Because for x bigger than 0, f prime is positive. So on open interval 0 to infinity, f prime is positive. And theorem says that, implies that the function is increasing on the closed interval 0 to infinity. Now f is increasing from minus infinity to 0, and f is increasing from 0 to infinity. How can I combine these two? Hence, f of x is increasing on the whole interval minus infinity to infinity, which means all real numbers. Why? If the function is increasing from minus infinity to 0 and increasing from 0 to infinity, can I conclude that it must be increasing from minus infinity to infinity? I can conclude this because of one of the examples that we did above, that it was saying that, recall, if f of x is increasing on A to C and increasing on C to B, then it is increasing on A to B. See example above, or C above. One of the examples we did today, we proved this, right? So based on this, if f is increasing on minus infinity to 0 and increasing on 0 to infinity, then it will be increasing on minus infinity to infinity. Okay. So let's do some more examples.